Hello all, I welcome you all to the 14th lecture in this course E698M. The last time we met, we spoke about thermodynamics and population statistics. And today we will do a short recap of what we saw yesterday. And then we will move forward to study a bit about spins and spin orbit interactions. So last time we saw about a bag having a collection of infinite particles. Each of these dots are a particle, and we saw that they can have independent position and velocities. And if I take a small collection indicated by this red dot here, if it has, let's say, n particles, and if I ask this question, what is the probability that the sum of these energies of these n particles turn out to be EI? And that is given by this particular function, where Z is called as the partition function, and e power minus beta is called as inverse temperature. So we saw beta is 1 by kBt. Kb is the Boltzmann constant, T being the temperature. So you can clearly see that you have this e power minus beta EI. So this is the Boltzmann's term, which is typically used in many of chemical sciences and studies that we have seen. Classically, you'll see always an exponential term which determines the probability, which is called as the Boltzmann's term. That's what we see here. Z is called as the partition function. There are several important uses of this partition function. Today we will see two particular examples of using this partition function and determining important properties such as the average energy and the free energy and such. Z is also a normalization factor for this probability. So we know that P of EI cannot exceed 1, and summation of all this P of EI should eventually turn out to be 1, right? Basically, the collection of these n particles should have some energy. And what is the probability? So basically this EI is one such energy, right? So summation of all possible energy should eventually give you 1. And what we have Z is exponential of beta EI, right? So basically what we mean is probability, summation of probability of EIs is going to be 1, right? And this Z is given as e power minus beta EI by e power beta EI summated over all possible energies is called as the partition function Z. It's important to note here that each of these particles, we saw there are multiples, infinite number of particles here, right? Each of these particles can have multiple energy levels, and each of these energy levels have equal probability of occupation, right? That's the fundamental assumption of the thermodynamic derivation that we did here. What we mean, we will show very soon later. Let's take each particle here. This particle, let's say it has some energy levels E1 to epsilon 1 to epsilon m. Each of these energy levels have equal probability of occupation, right? That's what we mean. In the previous derivation here, EI is continuous. So basically we were still talking about classical description. So what we mean is the collection of particles given in this red circle can take any available energy value. It does not have to leave out any energy value. It's a continuous distribution because we are still talking about classical particles. When we move to quantum particles, as we saw previously, the energy levels are discrete, right? Because the k values cannot take any value. We saw from Born-Warman boundary condition to tell you that k values have discrete values, and based on this k, the energy values are discrete. And the second thing is, if I have some infinite number of particles and few energy levels like this, each of this energy level cannot have infinite number of particles, right? Because if the particle is an electron or a fermion, no two particles can have all the 4 quantum numbers the same. 4 quantum numbers, I mean L, M, and S, right? This is what we saw. Describes the wave function of an electron in an atom, right? In a spherically symmetric potential, particularly a Coulombic potential, it requires these 4 quantum numbers. And we saw that because of the fact that if you have two particles which are indistinguishable, and if I swap these particles in these two different places, there are only two ways to swap it. And one way, if the wave function changes sign when you swap these two particles, they are called as fermions. What I mean is, I have two particles in two positions. If I interchange these positions, if the wave function takes a negative sign, we call it fermion. If the wave function takes a positive sign, we call it as bosons. And because it takes a negative sign, no two wave functions can have the same energy and all the four quantum numbers the same, because it takes a negative sign, so the summation will cancel out each other and give you a 0. We have a positive sign here, which means that you can have infinite number of particles in the same energy. They are called as bosons. We will deal with bosons a little later. So now let us, or last time we dealt with the fermion. The way to find how the fermions are distributed in energy, we took what is the probability of filling a single energy level in the fermion, right? So basically it is in this description. So let's say an electron can take some discrete energy levels, epsilon 1 to epsilon m, right? And we have several such particles in this collection. And these particles have to be filled in these energy levels. If I put one of them into this energy level, the second one obviously cannot go here, right? It has to go to the next energy level, and the other one has to go to the next energy level, and so on and so forth, because this is how it has to be filled. Now the question that I am asking is, taken some energy level EI somewhere here, epsilon I, what is the probability that this is filled? How do I find that? What I am saying is, it is a probability of an n electron collection with total energy Ej such that this guy is filled. Basically what I am saying is, if there are, let's say, m ways of distributing these n electrons in these energy levels such that Ei is occupied, the probability that that electron level is occupied is a summation of all such probabilities. Right? You have to think about this statement a little bit more deeply to understand this. Right? So if this is given, then the way last time I solved, or this is also shown in Ashcroft and Mermin, you can actually go and take a look at this derivation in the book as well. It is basically 1 minus the probability that that energy Ei is unfilled. That is what is given here, Eg. And how do I get a energy level which is unfilled? I actually take an n plus 1th energy level, assume that energy level is filled, and then take one particular Ei energy level out. And if I go through this derivation, I get this function f of Ei. Basically this is fi of n. I am writing it as f of Ei because this is the Fermi-Dirac distribution that we know very well about. If I plot this function as a function of energy, this is f of Ei as a function of Ei. It has this kind of a behavior at temperature T equal to 0, and at any non-zero temperature this will change symmetrically about this particular point, right? At higher and higher temperatures you get something like this, and this energy level is called as the Fermi energy level, Ef. This is the last energy level which is filled at 0 Kelvin. Right? So these are some things which you have already known. Now let us do some worked out examples for the uses of partition function. This is this is important because as we go through this derivation, we will also see what happens if you are allowed to fill more than one electron per state. One has to look back here, okay? If I ask you this question, we did this derivation, where do you think that we have used the fact that you can have only one electron per state? Right? So this will be something for you to think about. We have used this fact somewhere here in this derivation, which lets you bring to this particular format for the probability to have a particular energy level filled. Let's take an example of an electron which can take only two states. Okay, you can think of it as an electron, you can think of it as a spin level or whatever, right? Instead of having infinite number of states, let's assume a very simple case. I am having only one single particle, and that particle can have only two electron energy states. One is defined as plus delta by 2, another one is defined as minus delta by 2. These are the two possible energy states. If this is the case, how do I write the grand partition function? Not the grand partition function, just the partition function z. It is summation of over all the energy states e power minus beta ei, right? And ei energies is plus delta by 2 and minus delta by 2. If I do this summation, it is written as e power minus beta delta by 2 plus e power beta plus delta by 2. The summation of these two will give you a cos h. This is the partition function. Now that we have a partition function, how do I calculate the internal energy or the average energy of a particle here? In our previous class, we derived this expression. The average energy U is also written as the expectation value of energy E, is basically summation of EI, P of EI, right? And this we prove to be having this particular formula, minus d by d beta ln of z, z being the partition function. Now, instead of, it will be difficult to evaluate the logarithm of cos h, so what I did was, I just took e power minus beta lambda by 2 outside. That will give me 1 plus e power beta lambda, beta delta, right? If I take a logarithm of this, I will get minus beta delta by 2 plus log of 1 plus e power beta delta, correct? And if I differentiate it as d beta, I will encourage you to try this. I will get this expression. Now if I plot, this is the average energy, right? If I plot this average energy as a function of temperature, so where do I get temperature is from beta, right? So it has this particular form. It is not very visible. It goes like this. It goes at very low temperatures, it is minus delta by 2, which is the lowest energy level. So what it means is, at very low temperature, the electron would most likely stay almost all the time at minus delta by 2 energy. As you slowly increase the temperature, for some time the electron jumps up and again comes down, right? So that the average energy is now slightly positive. As you keep on increasing the temperature, it is possible that it will spend half the time here and half the time below. So it will asymptotically go to 0. So at max it asymptotically goes to 0. By that what I mean is, an electron in two level system at max can spend half the time at the excited state and the half the time at the ground state, giving you an expected energy of 0. Right? So this is a very profound example which we can solve using partition function in a very simple way. So we just now showed that if you have an electron in the two level system, something similar to this, it can at max spend only half the time in the excited state. Now let's take the second example, which is a quantum harmonic oscillator. We have seen this before. You have the ladder energy levels, each of them separated by h cross nu. The lowest energy level is h nu by 2, h omega by 2, and each one of them is another h omega addition to that, right? So if I have this energy levels defined in this particular format, and once again I do not have a collection of harmonic oscillators, but let's say I have only one harmonic oscillator having this many states. How do I do the partition function again? I use this particular equation. Z is summation over I e power minus beta ei, right? In ei I substitute this en formula, so I get this as the partition function. I do some little bit of math, so I will get my partition function Z given by this particular equation. There is one formula that I have used. This is some sort of an arithmetic progression. Summation over n, some term power n can be written as 1 by 1 minus that term, right? So this is a very simple mathematical trick, right? So once I have this partition function defined here, as we did previously, I calculate what is the probability that any state n is occupied. So here I have 1, 2, so on till energy n, some state n. What is the probability that state is occupied? Is 1 by z, z being the partition function, e power minus beta en, right? This is what we derived previously. And en is given by this expression, and ez we just calculated. When I did this, I'm going to substitute e power minus beta h cross nu as a. So when we do this, the probability that any energy level n is occupied is given by this formula, an into 1 minus a. Given the occupancy probability, what is the mean occupation of a state? That is the mean energy, as we did previously. We do summation over n, p of n. Right? So this gives me the mean occupancy of any state. So this, once again, I substitute p of n here in this equation, and I do a little bit of mathematical let's say reduction, and finally get the mean occupancy to be of this form. This is the famous Bose-Sainstein distribution. What we mean is, if I have an harmonic oscillator with energy levels distributed like this, the mean number of electrons, mean number of particles in an harmonic potential at any of the energy levels is given by this formula. You can see that it is slightly different from the exponentially decaying distribution that we have for any classical particle. If you have a quantum harmonic oscillator and we have a particle in the quantum harmonic potential, then the mean occupancy has this particular term. This is called as the Bose-Sainstein distribution. So from the first canonical ensemble example that we saw the classical Maxwell's-Boltzmann distribution, e power minus beta ei. Right? This is the Maxwell's classical distribution when the energy levels are continuous. We saw in the case when the number of electrons in any state can either take only 0 or 1 case, we saw what is called as the Fermi-Dirac distribution, which is given by 1 by 1 plus e power ei minus mu by kt. We derive this. And now we come with the Bose-Einstein distribution, which is the mean occupancy is given by 1 by e power h cross nu by kt minus 1. This is the Bose-Einstein distribution, right? So we have sort of derived all these things from first principles, and then given a density of states as we did in the previous lectures, and the statistical distribution of this at any given temperature, we can calculate the electron density and the free carrier density, which will be used for electron conduction and such, right? So now let's go back and then look at what we were supposed to deal today, that is the matter of spin. Till now we did not look at this particular aspect of an electron, that is spin, and now it's time to look at it a little bit more closely. You can draw a very simple analogy for spin. One is basically it is an equivalent of an electron or Earth going around the sun. So basically we have sun, and we assume that the Earth goes around sun in elliptical orbits, right? It has some orbital angular momentum. What is orbital angular momentum? It has some force and some r. So basically F cross r is the orbital angular momentum. It has some momentum across around in a circular orbit. It moves along a circular orbit across this particular point, right? So you have something normal to this. You have an orbital angular momentum acting along this direction. In addition to this orbital motion, the electron or the Earth also rotates among itself, right, about its center of mass. So basically Earth has an orbital angular momentum L as well as a spin angular momentum, that is a rotation about its own axis. The same way an electron rotates about the nuclei as well as have some rotation about its center of mass. However, people always tell you that you cannot take this analogy too forward because electron is known to be indivisible. if it is rotating about itself, one has to look at having each part of the electron having different uh, uh, orbital angular momentum, right? So basically, let's say it's like a spinning top. So let's say we have a top like this which is spinning. Each part of this top should have a different orbital angular momentum, right? But that is not what happens. We cannot divide electrons. So basically you cannot extend this analogy too further, but we can just use it to understand that the spin can be taken such a way that it can have only two different values, in the sense the spin quantum number cannot degrade. It can only change its sign from h cross by 2 to minus h cross by 2 in the case of an electron, or it can have 1 to minus 1 in the case of a photon, right? So only it cannot have any other value. The spin is an intrinsic property of the particle. It cannot reduce, it cannot expand, it only flips from one state to the other. All particles are associated with some spin, which is also used to explain why the indistinguishability of the particles can be arranged. So what we mean by this particular statement is that the spin, it always so happens that particles which have non-integer spins, for instance h cross by 2 is a spin quantum number, when 1 or h cross is also another spin quantum number. Particles which have a spin quantum number which are integers are called as bosons. Particles which have spin quantum numbers which are non-integers are called as fermions. And fermions always have a negative sign in the wave function expansion when we swap particles, right? So that's what we saw previously. So let's say the pi mesons have spin 0, electrons, as we saw previously, are fermions, have spin 1/2, photons have spin 1, delta has 3 by 2, and gravitons have spin 2, and so on and so forth. One can actually compare this spin quantum number with the orbital angular quantum number L, which can take any integer. For instance, it can have minus, 200, right? Because it's just a much higher excited state of an atom. But whereas spin quantum numbers can take only few energy levels, it cannot degrade from -3 to 2 and so on and so forth. So now let us take a look at a little bit closely on a spin 1/2 particle. And because the spin 1/2 can have only two values, which is h cross by 2 and minus h cross by 2, there are two different eigenvalues. And with respect to two eigenvalues, you can have only two eigenfunctions. We define two eigenfunctions to be in this particular form, right? So it's 1, 0 and 0, 1. These are the basis eigenfunctions corresponding to these eigenvalues. So we typically, by convention, note this as up arrow and down arrow, right? Because it is just like a spinning top. One spins on the left, let's say in the clockwise, another one spins on the anti-clockwise, something of that sort. When there are two eigenfunctions, the spin wave function of any electron can obviously take the superposition state, which has chi is alpha chi up arrow up spin plus beta chi down spin. Remember, the normalization criteria tells you that alpha square per beta square is always equal to 1. So basically you have two variables and the square of them should be equal to 1, right? And alpha and beta can be any complex variable. So you can actually represent them on top of a sphere as shown here. This sphere is called as the block sphere. These two variables, as we shown here, can be represented or taken to be in this particular form, which is cos theta by 2, and the beta can be taken as e power I psi sin theta by 2. It's easy to see that if we replace these two in this equation, this particular equal to 1 will be satisfied. And if we see here, theta is the deviation from the z-axis. So this is the z-axis. Theta is how far is the particle away from the z-axis, and the psi is the phase, is this rotation, right? So you take this and then you just rotate it. So basically, is it along this circumference, or is it along, let's say, the this circumference, or is it along this circumference? Right? These are the things that determines the let's say there are two. Okay, so basically there are two variables. One is how far it is away from the positive z axis, and what is its angle in the in plane direction. So there are two variables which can determine where the particle lies. The particle can always lie only on the surface of this sphere. So this sphere is called as the Bloch sphere. This is used to demonstrate entanglement and this an entanglement between two states and the spin states and so on and so forth. It's very important, but for the purpose of this course we will just leave it here, because later when we come back and talk about spin orbit interaction, this particular picture will be useful. So now that we spoke about spin wave functions, we can also define a spin operator Sz, because we spoke about wave functions chi up arrow and down arrow as well as the eigenvalues. You can define an operator Sz such that when it acts on the wave function, it spits out the eigenvalue h cross by 2 and gives you the same eigenfunction back. This is the eigen equation, as you know, right? Now, how does the spin interact with any other external functions? Spin does not obviously talk to electrical field. Spin talks to only the external magnetic field. So basically you can access the spin quantum number or spin degree of freedom in an electron by applying external magnetic field. And how does it work? A spinning charge particle is basically known to have a magnetic dipole, which is mu, which is given by some gamma, some dipole constant multiplied by the spin quantum number S. So if I have let's say some sort of an electron dipole given by this blue bar, you have mu which is along the axis of this blue bar. If I have a magnetic field B, the magnetic field acts to give a torque to this blue bar to rotate it along the magnetic field direction, right? So basically along this arrow. So it will try to rotate this particular red arrow to be parallel to this magnetic field direction. That is how the torque, that is how the magnetic field produces the torque on this dipole or torque on the electron, right? So if, let's say, we have an electron in an uniform magnetic field Z, it is known. I'm not going to solve it here because it is just too much detail, and if necessary, obviously you can always contact me and I will explain how it actually works. What happens is the spin is known to precess at a frequency which is called as the Larmor frequency. Remember, this is the Bloch sphere that I spoke about, right? So basically we have the Bloch sphere here, and this is on the circumference. This is at some point in the circumference. If I have a magnetic field B naught, this radial line is going to precess along this line, right? As we, if I go back here, let's say we have something like this here. If I apply a magnetic field along the Z axis, the electron will precess or move or will change the variables alpha and beta such that it rotates along this particular circumference line, right? This is what is called as the Larmor precession. This is what happens when you apply a magnetic field. It changes the alpha and beta value. It changes the way in which the upspin and the downspin are superposed in this particular state, right? Now that we understand spin and we understand what magnetic field does to the spin, now let us go and look at the effect of spin orbit interaction. This is a culmination of what happens when you have some sort of an inherent magnetic field in a material and what impact it has on the electron spin. Why this is important? Because most of the semiconductors that we talk about have this particular property, that the valence electron of the most of the atoms that we have contributions from mostly p orbitals, and p orbitals have non-zero orbital angular momentum value Cl. Why? So let's look at this. Carbon has 1s2, 2p, 2s2, 2p2. Silicon has 3s2, 3p2. Germanium has 4s2 4p2. All of them have 4 electrons in the outermost shell. And let's look at group 3,5 semiconductors. It has, let's say, gallium and arsenide. We're talking about gas here. Gallium has 4s2 4p1 and arsenic has 4s2 4p3. Right? So you can clearly see that you have the largest dominating contributions from the s orbital and the p orbital. But empirically, when you actually calculate the band structure using tight binding model, we saw this previously. Most of the semiconductors have 2 atoms per lattice point, right? You always have an FCC structure with a lattice with a motif. So in the gallium arsenide case, you have a gallium and arsenic in each lattice point, right? Something like this. In silicon, you have both of them being silicon. So how do we write the solution? We saw this in the previous case. You write the atomic orbitals as summation of atomic orbitals, each phi n as summation of atomic orbitals, and you put it in a block kind of a solution to give you the atomic wave functions, or to give you the electron wave function psi k, right? So when we take the example of gallium arsenide, it is almost always, it was shown by empirically as well as by several calculations that the valence band typically contains p-type contributions and the conduction band has s-type contributions, right? So what we mean is you have this summation of b and psi atomic orbitals, right? And when we talk about electron energy levels in this line, b is non-zero only for p-type orbitals, and when we talk about electron energy levels here, b is non-zero only when only for atomic orbitals which are s-type. So basically, if it is gallium arsenide, this is 4s and this will turn out to be 4p. Sorry, this will turn out to be 3p, right? Yeah. So what's special about 3p? Because as we saw previously in the wave function derivation for an atom with spherically symmetric potential, is that p-type orbitals have L non-zero. So basically L is an orbital angular momentum, which means that you have the nucleus and now the electrons now rotate around the nucleus at some velocity or at some momentum, right? This is the orbital angular momentum. For a s-type wave function, basically the L is 0, which means that the electron does not undergo this orbital motion. For a p-type orbital, L is non-zero, so it undergoes this orbital motion. And when you have an electric charge having this circular motion, you have a magnetic field which acts perpendicular to the plane in which it undergoes this motion, right? So basically it automatically gives you an inherent magnetic field. Instead of taking a magnet and putting over the material, the very fact that you have p-type orbitals contributing to the band structure already gives you some sort of an inherent magnetic field to the material. And when you have the magnetic field, it is going to interact with the spin state, right? As we saw previously, it will lead to precession of the spin. So in gallium arsenide, the top 3 bands are threefold degenerate. When we mean degenerate, we have px, py and pz. All these energy lines are actually degenerate. They have similar energy values. Basically they are 6-fold degenerate because each of these can take 2 electrons. Px, py and pz, each of these state can take 2 electrons. When there are no magnetic field, all of them are degenerate. Now the question is, what happens when there is a magnetic field, or what happens when there is a spin orbit interaction? What we mean by spin orbit interaction is that you have an electron orbital with L not equal to 0, and this electron orbital has some interaction which adds to the Hamiltonian H some spin orbit contribution hs naught, which is given by gamma. Gamma is the gamma is this gamma. Oops. Yeah, is the magnetic moment gamma, right? So basically H spin orbit interaction is gamma L dot S. L is the magnetic field and S is the spin, right? So basically L dot S is the projection of the magnetic field or the spin direction in the direction of the magnetic field. So when we have this kind of a magnetic field coming out about because of the orbital angular momentum of the valence band, spin is no longer a good quantum number. So we define J, which is called as a total orbital angular momentum. Total angular momentum, not the orbital, it's called total angular momentum, which is defined as J square is a summation of L plus S square. If we take the example of a p-type valence band, so P has plus or minus 1, L equal to plus or minus 1, and spin is plus or minus 1/2, right? So basically J can have plus or minus 3/2 and plus or minus 1/2. So this leads to two different energy level bands in a semiconductor, which is separated by this energy. This energy is called delta S naught, which is called as a spin orbit separation. So you have these two energy bands which have J equal to plus or minus 3/2, and you have this energy band with J equal to plus or minus 1/2. I will repeat, J is just the summation of L plus S. L is the orbital angular momentum and S is the spin. As we saw previously, L is plus or minus 1 for a p-type material, p-type band, and S is equal to plus or minus 1/2, right? So that gives you J is plus or minus 3/2 and J equal to plus or minus 1/2. Now when you have two something like this, the one which has the smallest slope is called as a light hole, and one which has a large slope is called as a heavy hole. And this is something that we saw previously. We will deal with this later on as well. And this band, which is spin orbit separated, is called as a split off valence band. So you have a light hole, you have a heavy hole, and then the spin split or spin orbit split band or spin orbit hole, spin orbit split hole, right? So this is the tight binding band structure for gallium arsenide. When we ignore spin orbit interaction, you have all the three px, py and pz being degenerate at the gamma point. But whereas if you include spin orbit interaction in the gallium arsenide, you can see here that you have a small spin orbit splitting here, right? And you have the light hole and the heavy hole here, and you have the spin split band. When we do the same thing for aluminum arsenide, you can once again see the spin orbit splitting. The spin orbit splitting comes about because you have the valence band which is made of p-type orbitals which have L non-zero. You have spin orbit splitting in silicon, germanium, gallium arsenide, indium antimonide, indium phosphide, gallium phosphide, and so on and so forth. You have the maximum spin orbit splitting in regions in materials having large atomic numbers, right? So if you see silicon and germanium has a larger atomic number than silicon. So you can see an increased spin orbit splitting between germanium and silicon. Similarly, you have antimony and arsenide giving you larger spin orbit splitting because you have larger L values. Whenever you have larger L values, it will interact more strongly with the spin values or the spin of the electron in these bands, right? So we will finish off this particular discussion on bands and spins and spin orbit interactions and occupancies and such by just comparing the different semiconductors that we use. The most common one being silicon. In silicon, the spin orbit separation is very small, as we see here. The topmost of the valence band do not match with the bottommost of the conduction band in K value. This is called as an indirect band gap. And it should also be noted that you have 6 equivalent dips. 6 equivalent dips at the X point in silicon. So basically whenever we calculate the density of states in the conduction band and such, we have to ensure that we make or add this to our consideration, that you have 6 equivalent values in silicon. In gallium arsenide, we have a spin split here because of the spin orbit splitting, and the topmost of the valence band and the bottommost of the conduction band match in the same K value. For germanium, once again we have a spin split, and the band gap is actually indirect, but the direct band gap is not too far as well, right? In silicon, the direct band gap is too far. In germanium, it is still an indirect band gap, but the direct band gap is also not too far. The another material which I don't know it will be of interest or not, it is aluminum arsenide, just taken here for an example. The band gap is much larger, it's 2.7 eV, and once again it's an indirect band gap semiconductor, and you can actually see the spin orbit splitting here in the valence band. Now that we have seen all these things, we can actually take this data and then go and do what we did in 614, right? So basically now we know what is the density of states, we know how to calculate the Fermi-Dirac distribution, and we can calculate the total number of carriers at any temperature T is given by integral density of states Fermi-Dirac distribution into d. This will be 0 to infinity, and depending upon how the density of states behave, you can calculate what is the carriers that you have, or if you know the carrier density, you can actually calculate what will be the chemical potential mu, which comes about here. F of E is basically 1 by 1 plus e power E minus mu by kBt, right? So mu is the chemical potential. I don't know if you will remember, there is some subtle point that we used and when we derived the Fermi-Dirac distribution. This is f of n plus 1 minus f of n. F is the Helmholtz free energy as we described previously, and this is the free energy in the situation when you have n plus 1 particles, and this is the free energy when you have n particles. So basically it is also written as dou f by dou n. So change in free energy if you add one particle to the system is called as the Fermi energy. It is, or you can also look at how much energy that you have to provide to add one particle to a system. The mean energy that you have to provide to add one particle to a particular system, right, at any given temperature. All right, so let me stop this video here, and the next time we meet, let's talk a little bit about using this Fermi-Dirac distribution and the density of states, and let's alter the Druth's model and then look at how semi-classically we can describe transport and how we can understand Boltzmann transport and so on and so forth. Okay, so thank you.